Hello, good morning, students. I'm SONU SINGHAL, and the subject is strength of materials, and the topic is mechanical properties of the materials. Now, we will study stress-strain relationship. The second is hardness, and third is effect of temperature on properties, and fourth is fluid properties, and the fifth is viscoelastic behavior of the polymers. Now, we will study step by step. The first is stress-strain relationship. Three types of elastic stress to which materials can be subjected. The first is tensile, stretching the materials. The second is compressive, squeezing the materials. The third is shear, causing adjacent portion of the material to the slide against each other. Stress-strain curve, basic relationship that describes mechanical properties for all three types, right? The first is tensile test. This is the specimen of the tensile test. You can see in the diagram. The most common test for studying stress-strain relationship, especially metals. In the test, a force pulls the materials, elongating it and the reducing its diameter, right? Left, tensile force applied, and you can see this diagram. The first diagram is applied tensile force, and the second diagram, it is a result elongation of the materials, right? And this is the tensile test specimen. You can see these figures, and ASTM, that means American Society for the Testing and Materials, specifies preparation of the test specimen, right? In the middle section, that is the gauge marks, right? This is the tensile test setup, tensile test machine. You can see this machine, and in this machine we have the tensile test. In the next, tensile test sequence, right? This is the figures of the tensile test sequence. The first figure is when the no load applied, right? In the second, the uniform elongation and area reduction, right? When the uniform elongation in the specimen, so area is decreased, right? And the third is maximum load, and fourth is necking. Necking means it is the reduced diameter in the middle section, and the fifth is the fracture, and sixth is putting pieces back together to measure the final length, right? Next, engineering stress. Stress is defined simply force upon area, where sigma is the engineering stress, F is the applied force, and A is the original area of test specimen, right? And engineering strain is defined in the test. E is the L minus L naught upon L naught, where E is the engineering strain, L is the length of n at any point during elongation, and L naught is the original gauge length, right? This is the typical engineering stress strain plot. You can see this diagram. This is the stress strain curve, and we know this by the Hooke's law, right? And in this figure there are two regions. The first region is elastic region, and the second region is plastic region, right? And in the next, elastic region in the stress strain curve, that is followed by Hooke's law, and Hooke's law says that sigma e equal to capital E into small e, where capital E is the modulus of elasticity, right? Material returns to its original length when stress is removed, and capital E is a measure of the inherent stiffness of a material. Its value differs for the different materials, right guys? Next, yield point in stress strain curve. As the stress increases, a point in the linear relationship is finally reached when the materials begins to the yield, right? Why is the strength property? Other names for yield point, that is the yield strength, yield stress, elastic limit. Plastic region in the stress strain curve. Yield point is the beginning of the plastic deformation. Stress strain relationship is no longer guided by the Hooke's law. As load is increases beyond y, elongation proceed at a much faster rate than the before, causing the slope of the curve to change dramatically. Right? Tensile strength. Elongation is accompanied by a uniform reduction in cross section area, consistent with maintaining constant value. Finally, the applied load F reaches a maximum value and engineering stress as that point is called the tensile strength, right? That is the F max upon A naught. Ductility in the tensile test, that is formula EL equal to LF minus L naught upon L naught, where LF equal to specimen length at the fracture and L naught is the original specimen length and EL is the elongation, right? True stress value by the dividing the instantaneous area into applied load, sigma equal to F upon A, where sigma is the true stress and F is the force and A is the actual area resisting the load, right? True strain provides a realistic assessment of the instantaneous elongation per unit length, right? That is L naught to L dl upon L, that is log L upon L naught, right? Next is true stress strain curve. This is the stress strain curve and define the true stress curve for previous engineering stress strain plot. You can see, and this is the elastic region, this is the yield point, starting of necking and end of the point is fracture point, right? This is the strain hardening in stress strain curve, right? Note that true stress increases continuously in the plastic region until necking. In the engineering stress strain curve, the significance of this was lost because stress was based on the original area value. It means that the metal is becoming stronger as strain increases. This is the property called strain hardening. Right, guys? This is the true stress strain in log plot. In log. So we can plot by the log stress and true stress curve plotted on the log scale. You can see this diagram. This is the figure. This is the graph of the stress strain. Right. Categories of stress strain relationship perfectly elastic. Right. This is the stress strain curve graph. Right. And the second is compression test. Compression test means applied a load that secures the ends of the cylindrical specimen between two plates. Compression force applied to the test piece and resulting change in the height and diameter. So you can this figure, and this is the compression test. We can compress of any specimen by the reducing of the length of the specimen, right? And this is the compression test setup. This is the compression testing machine, and you can see that this is a UTM means universal testing machine. In this machine we have two performance: tensile test or compression test. This is the engineering stress in compression. Engineering stress for compression strength is defined negatively. Negatively sign means that is the compression strength, and the formula is same: sigma equal to force upon area. And engineering strength is also defined, that is the H minus H naught upon H naught, since height is reduced during compression. value of E is negative. The negative sign is usually ignored when the spacing compression strains, right? And the last, stress strain curve in compression. So this is the stress strain curve for the compression stress. Thank you guys. Thank you.